technologies in electrical vehicles and hydrogen energy storage. Today, we are moving forward with session 7, which is another important and insightful session of our FDP. Now, it's my great pleasure to introduce today's distinguished speaker, Dr. Deepak Rodanki, Assistant Professor in Department of Engineering Design and the Indian Institute of Technology, Madras. Dr. Rodanki leads the Power Electronics and E-Mobility Laboratory at IIT Madras, where his research focuses on power electronics, transportation, electrification, electric systems, electric drives, renewable energy integration, and advanced energy conversion technologies. Dr. Rodanki has established himself as a leading researcher in the field of power electronics and e-mobility, contributing significantly to the development of innovative solutions for sustainable transportation and renewable energy applications. His work bridges fundamental research and practical engineering solutions addressing contemporary challenges in electric mobility and power conversion systems. He has authored numerous high-impact research publications and has received wide recognition from the global research community with thousands of citations to his scholarly contribution. Today, we are privileged to benefit from his expertise and insights. And this session will provide valuable knowledge and inspiration to all the participants. I sincerely request all the participants to actively engage in this session, interact with resource person, and make the best use of this learning opportunity. On behalf of the organizing persons and participants of the faculty development program, I extend warm welcome to Dr. Deepak Rodanki and invite him to deliver his expert talk.
So very good morning to all. Something which is also new for me. PhD student. So this topic is also new to me. So I am going to present on power conversion system control for yellow and green hydrogen. Okay, like this. So we're going to talk about what in terms of transportation. So I give you a brief about the transportation requirement because one of the main challenges that we have with conventional passenger vehicles that we have one concern will be the limited facilities because you can see that because of that there will be significant work going on. The second thing is energy efficiency. The efficiency is the very important thing. The third one that we have is environmental pollution. So these three are the three major problems that we try to shift from a conventional transportation system to a electrified transportation system. Okay. So everyone knows what we go with electrified transportation systems where we find an advantage that we have reduce the carbon emissions. So that is the main thing, and you don't need a more number of moving parts like a conventional light vehicles, and you will have a board which I talked about previously also high well-to-wheel efficiency. Okay, so well-to-wheel efficiency is the one that what is the energy required from the starting from the extracting from the well, what will be the output that you are going to get at the wheels. Okay, so that's well-to-wheel efficiency. So it is not just a conversion that starts from the vehicle tank to the wheel, and it should be from the well to the wheel. Okay, so where we consider that for ICE vehicles will have a petrol tank and a magnet at the wheels, and you are going to get the well tank efficiency starting from the extracting of the material or the raw materials or fossil fuels, and that you're going to extract and transmit and distribute it to the petrol pumps. Okay. So when it comes to the electric vehicle, the procedure is something different. Okay. We may call that electric vehicles are more efficient, but however, we have to consider not from the source. So source could be something like you may have energy source that could be from a battery, and it could be some fuel cells, and you can also use something like capacitors or high. Okay. So this I can show that energy supply units. So energy supply units for electrified vehicles, which could be from the battery. So that would be battery powered vehicles, and if it is from the fuel cell vehicles, and there are cases where super capacitors, when you want to have frequent charge and discharge, you can go with the super capacitors where you have high power density and low energy density. I'm going to talk about the cost. Okay, and then you can also have a flywheel or magnetic storage systems. So based on this, you can clarify the type of electric vehicles in the based on the energy supply units. Okay, so most probably everyone knows about that. When we talk about electric vehicles, it's all battery powered electric vehicles, right? Everyone agrees with this point? So we have a vehicle that means the battery powered electric vehicles, or you may have some hybrid electric vehicles, which is the combination of internal combustion engine plus battery powered. Okay, but there is a need that for the batteries that we consider here. So we need to utilize these batteries. Mostly we are going to use a lithium-ion batteries. Okay, so this lithium-ion batteries you're going to need. So this has to be get from the other materials. So this is not available in India. Okay. So when we have to get import from the countries like China, so the cost of these batteries when you buy it from India, it is almost $200 per kilowatt hour. But if it's for China, they are $90 per kilowatt hour. So you can see the difference. They have a resources, and the way the cost of the batteries are very less in the chain. But when compared with other countries, even US, Europe, or India, it is costing around $200 per kilowatt hour. So now people are trying to get the alternatives, not to rely on just on the lithium-ion batteries. So they are finding the other variants of the batteries. For example, solid-state batteries with the combination of sodium sulfate or zinc combinations, or there is a mixed combination of sodium and zinc. And there is also called other variants of the batteries. They are also explained where more of chemistries having placed in the dwellings. Okay, but there is another way of also. Sorry, there is another way of also having the vehicles where you can do with the fuel cell vehicles. Okay, so the fuel cell vehicles where we need a hydrogen for to have a what to have an ingredient or requirement for a fuel cell vehicle. So fuel cells are also started before, but the problem with the fuel cells is the storage of hydrogen and the generation of hydrogen is a big problem. Okay, you need to have a big cylinder or place in the vehicle, so where you need to store the hydrogen. Okay, so the problem, how do you store the hydrogen? You can store the hydrogen either in the liquid form or in the gaseous form. So we have to see that the form and storage of hydrogen, which is to be safe and reliable. So that is the other challenge, especially based on one is on storage aspects, other is on the generation aspects. The fuel cells are not predominant compared to the battery power vehicles. Okay. So, however, there is significant need or things that can also be done with the fuel cell vehicles. Okay. So here fuel cell vehicles, when I talk about this energy efficiency. Okay. So there is another important aspect. Okay, so let's consider that a simple electrified vehicle. You have so this is a simple block diagram of a so I have considered the wheel and the transmission. You have a machine, electric motor. So we need a mechanical work point the wheels. So we need a mechanical energy at this point. So the electric motor which converts from an electrical energy into mechanical energy. So in here we need a electrical power. It could be AC or DC, depends upon the type of the machine that you are going to use. So most of the machines that you're going to see are the AC machines. I think Dr. Gautam would have been talked about the different types of machines yesterday. So most of the machines that is predominantly used for electrified vehicles are the PMS machines. But however, the government has pushed to go with a magnetic field machines because the same problem with the batteries which I am talking about now. Because you need to have a metals that is not available in India, so we have to rely on the countries like China, and also there is a price. Okay, so price is going to change frequently, and you have to pay whatever they are going to give it. So the government has imposed to develop the magnetic field topologies, machine topologies for this application. Okay, so I think some of the things that is already at this point, so I'm not bringing that topic again on the machines, but this is the same problem that we have with fans. Okay, so here you need to have the AC power. So if you are using an AC machine, so let's say instead of EMS machine because everyone is using, so I need to have an AC power. So the energy supply units which I am talking about that could be a battery or a fuel cell or a supercapacitor or a flywheel or magnetic storage systems. Okay, so these are all things mostly they are going to develop DC power. We need conversion from DC to AC. So we are going to use an inverter or a power electronic converter which converts from the DC to AC. Okay, so I think you might have clear with the points where everyone has talked about this part. Okay, so now let's focusing on something on these energy supply units. So energy supply units, if you are using a battery powered vehicles, it's a battery, and you are using a fuel cells, there is a fuel cell vehicles. Okay, I hope everyone is clear up to this point. Okay, so the question is, what would be the characteristics of these energy supply units? So how do you choose what type of energy supply unit that you are going to set? Anyone? So all you know that I'm going to use a battery powered vehicles or fuel cell vehicles. Okay, but what is the advantage and disadvantage with these vehicles? I just want to know with respect to energy supply units.
People have more basic
Power bills. What else? So how do you distinguish between these energy supply units? How do you going to set? So the first important point that we should talk about range. That means mileage. If you want to have more mileage, what should be the characteristics of our energy supply units? energy supply unit ESU. So what should be the characteristics of energy supply unit if you want to have a more range? That is my name. So that means a given time it should deliver the high energy. How is going to calculate energy of this ESU should be equivalent to this into dt. That means what are the power that is required? It should deliver that duration. So that means energy is important. So we're going to talk about with respect to the range of energy density. Okay. So the more energy density, more mileage you are going to get. And what about this acceleration and deceleration? So what is this? Acceleration and deceleration. What type of characteristics are required for acceleration and deceleration?
High power short time.
That means every short interval of time you should deliver the high amount of power. That means the power density is significant. That means higher the power density, better would be the acceleration and deceleration capability. So that means if you want to design an energy supply unit for electric vehicles, if you are talking about the application where you want mileage is more dominant, what kind of energy supply unit you should select? The energy supply unit which has more energy density that to be selected if you are looking for the mileage. So if you want to have a high acceleration and deceleration capability, you should select with power density. For example, you take an example in normal highway. Okay, so we can take what is the highway here? From 16. So this is Bhimavaram to Bhimavaram. Complete express highway. Okay, so average speed should be maintained around 80 kilometers per hour. So you don't have start or stop operations. That means you don't have a frequent rise and frequent stops. We don't have. So you have a profile. So which is having a highway drive cycle. It is always going in a flat with 80 kilometers per hour. So what should be the characteristics of this energy supply unit?
High power.
So we are talking about only mileage here. We are not worrying about acceleration and deceleration. So the system that we have, we should have high energy density. We need not to worry about the power density of the energy supply. For example, you have a frequent stop. Okay. For example, you take a municipal truck, electric truck you want to do. So it has to collect the garbage from each house. So what would be the drive cycle for that kind of truck? So it will be a flying wheel. You're going to rise, then again you're going to decelerate and stop. This is ideally a flying wheel kind of drive cycle. So what would be the need? What type of energy supply unit is required here? Power density. What should be the energy density requirement here? Not required. You don't need any energy required because it's just for acceleration and deceleration. That means you are going to discharge as well as charge. Ideally, you don't need an energy here. Only the power requirement. Here we have Only energy requirement, there is no. So can you give the examples where I can use for hybrid drive cycle, what kind of energy supply unit I can use, and for this, what kind of energy supply unit I can use. Or I will have one more kind of drive cycle. It is something of, it is going to have an acceleration, deceleration, doing that. Or you can consider the city drive cycle. What kind of energy source I can use? I hope everyone knows about drive cycle. So I have not given this coordinate here. So drive cycle is with speed versus time. So how much speed the vehicle is going with respect to the time is called what is called as drive cycle or driving time. Anyone? So I have defined the 4 energy supply units. So can anyone mention here? Yeah, correct. Supercapacitor will have high energy, and they don't have energy. So they can easily charge and become like capacitors with the higher capacitance. Okay? So the off is where energy can store and it can be released. So for this application, supercapacitors alone can solve this one. Don't need a battery. What about here? Hybrid drive cycle. Hybrid drive cycle is good for the internal combustion engines. So where we require more minus, we don't want more the acceleration and deceleration. The moment you move for the acceleration and deceleration, the fuel consumption will be very high. So if you go with a constant speed or cruising speed every time, you will get better mileage even for the high vehicles. For this one, batteries. What about this? So what did you try saying? The city drive cycle is prefer to have a battery power vehicles. For highway, it's good to have a fuel cells. So how do you conclude this part? On what basis I have concluded this? So for that, I want to compare the different energy supply units. So we should compare with respect to energy density and the power density. So energy density I can represent with respect to weight or mass or with respect to volume. Right? That means by kg or liter. This is mass or volume. This is with respect to liter. Okay. So when you see this part, there is a plot called Ragone plot. You see here? So I have plotted with respect to specific energy versus specific power. This is with respect to mass. So I will have an energy density that with respect to liter, that is with respect to volume, that is liter, and power density also with respect to liter. When we represent with the specific power or specific energy, we are going to represent that with respect to mass. Okay. So here you can also conclude some of the important things here, right? So if I use the supercapacitors, we have a significant power. So I can use the supercapacitors for the municipal trucks, where I have a only acceleration. I can able to do that. Like we don't need a backup because it is going to accelerate. You select your supercapacitor based on what is the energy requirement or energy discharge and energy charge during decelerations. Okay. And for example, you see for the fuel cells. Fuel cells are ready to high energy. So it has more mileage than the supply. So this will be a component added to the internal combustion units. So that means I can prefer this one for the okay. And you see the combination here. That is, so it has a medium specific power, specific energy. That means you use something further. Where you have a both for magnet as well as that means a single energy supply unit may not be able to sustain for this. Okay. So now when you want to develop a fuel cell vehicle or battery power vehicle alone. So what is that we are going to compromise on that? So when you use fuel cell vehicle, what is the acceleration and deceleration capability? Because it doesn't have a specific power. So you may not be able to get a high acceleration and deceleration. I may not get like Tesla car. You get 0 to 100 kilometers in 1.9 seconds. 1.9 seconds you can able to when you press the acceleration pedal. It comes from 0 to 100 kilometers per hour in 1.9 seconds. So I cannot get the same performance with the fuel cells. Okay, I'm going to explain what are the different types of fuel cells vehicles are available in the market. So what is that I'm going to compromise on when I go with fuel cell vehicles? I may not get good acceleration and deceleration capability. Similarly, when I go for the battery power vehicles, I'm going to have an acceleration and deceleration capability and also mileage is what you get for the same for the fuel cell. You're going to get less. You can see the difference. That means you're going to compromise on the mileage, but you're going to get a reasonable acceleration. Then what could be a solution for this? If I want to get the same acceleration or deceleration capability, I have to enhance battery power vehicles with more battery pack, or rating should be increased to compensate to get that enough acceleration and deceleration capability. So what is the solution for this? Solution could be hybrid because we know this the Godic law. So I can combine when I want to use fuel cells, I cannot use fuel cell at all. So I have to make a combination of fuel cells with the battery, or it would be good if I combine fuel cells with the supercapacitors. So mine will be provided by fuel cells, and the acceleration and deceleration capability will be performed by supercapacitors. And another way, if you don't use the batteries that do a frequent acceleration or deceleration mode is required a frequent charge and discharge. It is going to affect the battery life. Okay. So even in the battery power vehicles, it is always good to have a combination with the battery power vehicles plus supercapacitors, where batteries are able to get a good mileage, and the supercapacitors will going to provide a good acceleration and deceleration. And during regenerative braking, we will try to recharge your supercapacitors rather than doing in a fuel cell as well as the lithium-ion batteries, where you can avoid frequent charge and discharge. Okay, so if you see in actual scenario with energy supply unit, I would prefer to use a fuel cell with a combination of a supercapacitor to get good performance, overcoming the range anxiety. At the same time, I can use with a better acceleration and deceleration capability. So I hope everyone is agree with this, right? So, so you can have a combination. So I can have a combination of these two. Would be a good solution, or a combination of these two would be a good solution. So what is that energy supply unit should have a characteristics? It should have high specific power density, high specific energy density, less maintenance, and you need to have a less weight and cost. So this is the ideal requirement, but however, none of the energy supply units able to meet this all requirements. Okay. So now for battery power vehicles, we need a charger. So this energy supply unit is a charger. For fuel cell, fuel cells here, we need hydrogen here. Now charging infrastructure for batteries is also a big problem for us. And now generating hydrogen, and the storage of hydrogen is a big problem. And storage of hydrogen in such a way should be safe as well as available. Okay. So these are some constraints that we have with the fuel cells. Because of these reasons, we have a problem with both fuel cell vehicles as well as battery power vehicles. So I hope everyone is clear with this. But considering the part where I can see as a theoretical aspects, so I am going to get a better mileage and better acceleration capability if I combine fuel cell with a supercapacitor, which could be a good solution for the future transportation sector. Okay, because I don't need batteries that will be manufactured and recycling of batteries, and also I need not to have a battery charging infrastructure. Okay, but the problem with the fuel cells is about the storage and generation. So there is another important thing that we should also look into that. So that would be like about what kind of, how much energy that is consumed while doing this process. Okay, so you have a battery charging system and also you have a hydrogen generation system. So in both cases, you need an electricity to generate that. Right? You should rely on electricity. But where is the electricity? So that we're going to express with respect to the efficiency, which we call as a value tank efficiency, or value battery, or value fuel cell efficiency. So where we have to use some kind of energy to get hydrogen and to charge the batteries. Okay, so there is some comparison, but however, it would be use a hydrogen, it requires less energy rather than charging a battery. Okay, so that's one way. It would be good if you generate hydrogen from electricity because it takes less energy compared to the battery power vehicles. Okay, so what is that we're going to generate hydrogen? A simple formula that you take a water, you divide hydrogen plus oxygen. So that breaking of the water, you need some electricity. So that power you have to get in the way of the electricity, or you have to depend from the grid or any other resources. Okay. So now the question that we have in the here is hydrogen fuel cells is a sustainable alternative to the battery powered electrified vehicles. So what are the challenges that we have? Can it replace the battery powered vehicles? So how many will go for the fuel cell vehicles and how many people will vote for the battery powered vehicles? Anyone? Any participants want to answer this question? I want to listen more answers from you because even I don't know the answer for this question. I just want your perspective. How you going to think about what are the things that based on that, how you look the future transportation application. Do you prefer going with the fuel cell vehicles or battery powered vehicles? Means say cost. Fuel cell are costly. Okay. Any other answers?
Safety.
Safety. Okay. So do you think batteries are safe? Any other? There is a lot of analysis. So many in engineering, no one wants to take initiative. The first floor people. No, no, I'm not going to school you, just I want your opinion. So, anyone? Yeah, fuel cell and battery you can mix. That is what one of the possible solutions that we have. The problem is the fuel cell is very expensive, batteries are less expensive. If you do that, that will be double the cost of your rice. Vehicles. Do you think stars or businessmen will buy it? Rest of the people they don't, because they will also buy it for their since it's a cost. Any more answers? From anyone? I want to listen more answers so that I can also play in a better way. So if there's more discussion, then we can go into that and we can discuss. Yeah, minus fuel cell will get more mileage. That's what we discuss. Fuel cell will better in terms of mileage. No doubt about it. So that we can able to get heated cell. So this graph says that fuel cell will give better mileage than the battery powered vehicles. Now if you answer something, I can able to clear the doubt. But battery chargers also we have lack of charging infrastructure.
Because in minimum and for fuels it may be high outside that very low.
Yeah, because there are no initiatives for doing this. You see in 2020, hardly have 900 charging stations in India. So now you can see 10,000. So because government have taken initiative to do that.
It's to be emissions in case of yes, case of that.
Yes. So that there are some studies that has been done. The fuel cell vehicles have a better battery efficiency compared to battery.
You are getting it from LCD.
So LCD required to generate this hydrogen is also less compared to a charging a battery.
For charging batteries more filling of
So one of the problems that we are facing, there is a very good point. So for battery charging, you need hours. Okay. So anyhow, Dr. Harris is going to talk about chargers. You can ask this question to him that fuel cells are better than power vehicles. But you're talking about charging, it takes 8 hours, 10 hours to charge. But you can just take like LPG gas, you can between your tank and this. It's hardly Production of hydrogen is somewhat difficult. Production, the first important thing is the production of hydrogen, storage, then keeping them for particularly temperature and shape, whether you do it in a liquid form or gaseous form. And how do you store the hydrogen? You store that in H2 only, or you will combine with the hydrogen. So these are the questions that is there. Anything else?
Safety wise,
Safety is big challenge because the hydrogen cylinder will be placed inside the vehicle. It occupies more space, and you can see that another way. This also adds to the mass of your vehicle. That means the power train has to be a little more oversized compared to that. And that depends upon the type of the vehicle that you are talking about. I cannot generate a fuel cell vehicle for a two-wheeler vehicle. Right? So I have only option with models. That is for a vehicle for two-wheeler. I cannot go into the market with a fuel cell vehicles for a two-wheeler, three-wheeler market. So that means India almost 60 to 70% market will mostly rely on battery particles. But what will be the effect on your light, medium, and heavy duty vehicles? So if you compare battery powered vehicles and fuel cell vehicles, you have a lot of advantages in the fuel cell vehicles because you have a bigger battery pack, you need a bigger charging systems, or the power rating of the charging system where we are talking about the megawatt chargers. So those who have listened to my previous lecture, which I gave last month, so where I was talking about the megawatt charger. Okay, so you need a bigger charging infrastructure for that case. I don't have that problem with fuel cells because I need not a very longer duration. I need not a bigger battery packs. And the problem is that we will have also recycling of the battery packs. There are other aspects that we are going to get. The question that we get comparing the fuel cell and battery power, is it a green energy solution or a zero carbon emission solution?
these renewable it is green. Hydrogen production is used.
No, that's what the challenge that we have. I'm not saying that it's completely a green solution. So we have to make a hydrogen production a green solution. That's what we're going to discuss today, green hydrogen. So one of the topic. So what are the other things? Students are here. So you don't have doubts on this fuel cell vehicle and electric vehicle. So you go into ask ChatGPT to which one I should select. The vehicle battery company will do all the things and you will decide based on it. Or you have YouTube videos having fuel cell versus battery powered vehicles. You will watch that videos and see. Correct? The question that I asked is already there in YouTube. Fuel cell versus battery powered vehicle. But they talk about actual systems, not on the technical part. So I want more answers from this. So this, when you give more answers, I can talk about more in detail. So the challenges that we discussed are about the storage and the generation. And the market segment that also we talk about. So it will be good if you go for light and medium duty or heavy duty vehicles, not on the two-wheelers and three-wheeler vehicles. So it will be good for cars, buses, trucks. So it will be a solution where it runs in highway, especially for electric trucks. This is a good solution where you trucks will travel in highway. There will be, if it is stopped, it will have some call time of 5 hours or 6 hours. Trailers will take rest for sitting that time. So you don't have a serious problem with the frequent start and stop. So in such cases, fuel cell vehicles are better than the manual power vehicles. And you can have this fuel refilling stations at some stoppage points, or you can make a fuel refilling stations as part. You will have petrol bunks where you can replace the petrol bunks with a fuel cell vehicle refilling stations. Okay. Is there any other thing? Okay, so I'm not happy with the answers, questions or answers that you asked. So let's go in detail about people who started with the fuel cell vehicles. So the first fuel cell vehicles started in Japan, right? So last month I visited Japan, so I visited this Toyota plant, Nagoya, where they started this in 1928, and they finished their first IC engine in 2 years. So 1930. 2 years they built the internal combustion engine. In 1928, 1936. But we are unable to do a project also in 2 years. Right? You can see the dedication, support from the government. And they also recently I was able to see what is the complete structure, what is there inside the Toyota. Okay, so this is the first version of fuel cell vehicle which was commercialized, and then Honda also started with FDX Clarity, and also the first fuel cell was also started with the General Motors, especially in the Canada. There is a company called Ballard, so they started the fuel cell manufacturing. The first manufacturing company in the world was in Canada, which was Ballard. So that was in the Vancouver, Canada. Okay. So where they started working on fuel cell, they invested so much money on the fuel cell vehicles before going with the electric vehicles. But the problem that they found is they were able to generate a fuel cell vehicle, but the problem is hydrogen generation and the storage. So this becomes a big problem, and they close the plant. So where our study was actually funded by the General Motors, where I did the PhD. The same university was funded by the General Motors, which is developed from these electrified vehicles, fuel cell vehicles, and they paid and they started doing research. Okay. So our university was very famous for automotive and electric vehicle technology, where the initial General Motors electrified vehicles research was started. Okay. So then Hyundai is also started recently. So these are all long back, but Hyundai recently has done this is very good with a zero emissions. They are claiming getting zero emissions. So these are the major things where they started with fuel cell vehicles. And also mentioned that it will be good for trucks and buses. Do you have any such kind of models or such kind of models in India? Can anyone say that? Any bus or truck that was using a fuel cell based? Yeah, now people are going with hydrogen train. That is good for. Let's not talk about this. If I want to talk about this, I'll take 1 hour on just for this. Okay. I don't think so. That is a suitable initiative to go with hydrogen. Because already you have getting the why you want to again generate hydrogen and store the thing that is required. You don't have an electric line, right? Where only diesel locomotives are there, they can replace with the hydrogen based. So other than that, you don't need a hydrogen powered vehicle railways like India, because most of things are electrified. You don't need a hydrogen based railways. just to show the initiative, they will have done something, but I don't think so that way. But there are something you can see in the hydrogen-based railways could be a solution where you can see there was the repairs that going to done on the tracks where you don't have an city or radiograph line, where you can have it two-core systems where they can keep all tools and they're going to for the repair of the electric tracks and all. Where the hydrogen power maybe could be a one solution. To develop the powertrain. Because powertrain is same. So I talked about here that energy supply unit is different, but the component the subsystems are same. So maybe you may need to have different types of power electronic converters to be different to interface in electric motor the energy supply equipment because to consider the battery will have high voltage and lower current level, but you go with the PSS, lower voltage, higher current level. We need to have a more of a gauge converters for the PLCs for battery to need a voltage source based. Apart from that, we have the same motor, same gauge systems. These are all things are same. Only the interface is going to change, and based on other protection grids. For example, you're using a battery, you need to have EMS. And the communication between the powertrain and the vehicle control unit to the VMS. So this parts are going to change. Okay. But also there is a fuel cell monitoring system and management. That is also an electrical controller that we have to do on the fuel cell, and that also has to communicate with the vehicle control unit. So these parts are almost same. The only thing is you will have a change in the energy supply rate and the interface. Interface is a power line, so power line engineer can do it. But the problem comes with the energy supply. Okay, so now when you see from the overall from the battery power vehicles or fuel cell vehicles, the complete system is almost done. Right? But the problem comes for the battery, you need a lack of charging infrastructure. So what is that? To finally come to the point, we have problems. Batteries, is charging infrastructure and the charging time and the battery degradation. These three important points that we should do. And you also have fuel cells, hydrogen generation, and hydrogen storage, and hydrogen state. So these are the problems that we have. So you have pros and cons for both battery and hydrogen vehicles. So they are also nothing problems here also. So which problems that we are going to address? That could be a feature of your transportation system. Okay. So now our job is to solve this problem. So already the battery vehicles, there was an initiative started to go with developing a charging infrastructures. You can see that where 900 or 10,000 the charging infrastructure and is going to come with the 200. That means you see that at least for 20 vehicles you need one charger. For each 20 vehicles you need one charger, but now we don't have one charger for 100 vehicles. Okay, so it should become 50 to 20 vehicles. You should have one charger.
Each month, battery swapping also. Battery swapping.
Yeah, battery swapping. I'm not going to talk about battery swapping because I'm not a fan of battery swapping, which I discussed before. Maybe you not because battery swapping you need to have same voltage, current, ampere hour, and also that the battery that you are used by one driver will be different from the other driver. So the battery implementation is something different. And also there is an important thing that you should also look at into battery charging. You should not charge your battery to 100%. So you have to maintain that between the 30 to 80% of SOC. That means the moment you are using battery, you are charging to 100% and discharging to the 0%. That means you are going to use one charge and discharge cycle there itself. And you are going to spend a lot of money from the battery doing that. And you should, each one has to have two batteries that should be there. And the energy operator has to invest a lot of money in this battery. One for the battery and the other charging infrastructure. So it would not be a good solution for this.
Battery stored vehicle, permanent of recovery of energy. See, reverse process and store it in the battery. Fuel cell vehicles is it possible?
Yeah, that's very good question. So you cannot again pump at least in the power that to the fuel cells because it's a conversion process, not a storage. Fuel cell requires an energy conversion device, not a storage device. So battery is a storage. You can reverse pump the energy. That's what we are doing in the charging. Especially in the regenerative braking, you can pump the energy and store that into the battery. But fuel cells you cannot do it. Right? So that's why when you want something like that, you try to utilize this supercapacitor hybrid version that is also that you can get enough acceleration and deceleration. So that has to be done by supercapacitor. Supercapacitor is cheaper and more reliable compared to a battery. So when you want to have a energy requirement, use fuel cells. When you want a power demand, use a supercapacitor. So that is one important thing that fuel cell alone may not be able to get in that. You can see that they have not used fuel cell, but they use the battery. So that was battery was sized to get acceleration and as well as the get the power during regenerative operation. Okay, so these are something and Tata Star was one Indian made, but however that is not successful. And there are some fuel cells from China. They are also producing that, especially in Bangalore. KSRTC have almost 10 to 20 fuel cell buses. So they are doing for the long trips rather than the short trips. If you want to have short trips, especially for city driving cycle, it's good to have an antibody mix. When you go for the highway, better go with the fuel cell. That means the single solutions may not be sufficient to meet all the requirements of our transportation. So India is diverse, not only by releasing cash or population, but it also depends on vehicles. The two-wheeler vehicles, three-wheeler vehicles, the four-wheeler vehicles, and there are different variants of vehicles. Okay, so that is other important thing that we should do. So are we really go with the only battery power vehicles? Then we have to build the charging infrastructure. Or you want to go with the fuel cell vehicles, you have to have a system where you can generate hydrogen. Or if you want to have mix, then you should have a charging infrastructure as well as hydrogen generation stations or hydrogen refueling stations. So what would be the cost? So this is a question of front of us. So we have to decide what kind of transportation that we want to promote. Okay. So single solution may not able to address all the problems. Good model, good business model would be a combination of fuel cells plus battery power vehicles. Okay. So now these are the some of the things vehicle type. What would be the motor? So there 130 kilowatt. And use the battery. They are not using a fuel cell. So you can see that they are using a battery. This is for the acceleration, deceleration requirement. And the fuel cell could be used for the bikes. Here also I think you can see somewhere this is the fuel tank. This could be the battery. So this is the battery. This is the power converter. This is the hydrogen storage tank. This is the battery that is fixed. Small battery, you don't need a big battery. So this is designed utilized for only for the acceleration and acceleration requirement comes. You have to switch to the battery mode or deceleration, that is regenerative braking capturing. You have to use the battery. That means here there are two sources. You have to have a coordinated control between these sources. Okay. Those who are working in microgrids, you will have multiple sources. People work on coordinated control. The same kind of control you may also require to control fuel cell, battery, fuel cell also. Okay. So that how you are going to differentiate that. So you have a power demand. So that power demand could be something like this. So it can be divided into the average power demand plus peak power demand. So average power demand is going to determine the magnitude. Peak demand is determined by the acceleration and the deceleration. Okay. This average demand that we can able to size with the fuel cell. And the peak demand, it is required a supercapacitor or a battery. So I have to make a strategy. That means I have to use some kind of low pass filter where I can get only the average value, and I can even get a high frequency filter where I can get only the low pass high pass filter to get the peak demand. Okay, so there is a coordination control has to be done between these sources. So that other control complexity is going to be increased when you have a hybrid sources. Okay. So now, whenever I discuss the same thing with a Toyota design, you have electric machine, power converter, and the DC-DC converter. So this is a lithium 9900 battery they are used initial version. Now they have replaced with a lithium ion battery now. And you have between high voltage to low voltage DC to DC. This is same. So this part is almost same. The okay. So any questions here? So when you see here, this is the important point. So this is the architecture of fuel cell arrangement. You have a huge tank, and you will have a hydrogen pump, and there is a hydrogen storage, and there is a water in the pump. That means, so this is an onboard hydrogen generation. That is it. Giving water, you are going to use some power, the socket to get generation of hydrogen, or you use a hydrogen gas storage there, and you can do that. Where you have types of systems where you have an onboard outboard chargers. Similarly, you can have an onboard generation system, but you cannot generate more there because it occupies more space. Mostly it will be outside, and you can going to store the hydrogen. Because I'm going to see explain this how this is required. So here for fuel cell you require hydrogen, and you have to have an oxygen required, and you're going to use water plus electricity. So this electricity used for the propellant. Okay. Any questions? So any questions? So there are some kind of go with the emission. That means the hydrogen generation should be of completely green, and we want to improve the efficiency and the heat efficiency. The heat efficiency, that means the thermal management about the how you are going to reduce the losses in the system, how effectively you can maintain the temperature for the battery pack as well as the hydrogen storage. So their targets is more towards these aspects. So that makes work on something on to have a good onboard powertrain, that to have getting a high efficiency as well as good thermal management. At the same time, they want to generate hydrogen. It should be more of zero emissions. So we should get a green kind of hydrogen that we want to generate. Okay. So there are some stats, the requirements they made. So they started with a volume and power density. They were able to get with the 3 kilowatt hour per liter. So that is the stat. They could be able to reduce because the power density is also important because one with respect to the volume because we have space, and also that if you have more weight, that is also going to add sizing of your power tank. That means bigger power tank is required to have drag your these components plus the protection and also to work with the resistive forces on the vehicle. Okay, so this is the version of fuel cell tank, but I am not going to explain on this area. So I don't know anything about this. I just want to show a picture so that you will get an idea of it. So you have a fuel stack, the hydrogen supply equipment, and this is all the powertrain. So this is powertrain. This is the gearbox, and then the oxygen, then hydrogen supply, and you need to have this down there. You need to generate hydrogen plus oxygen. So this electricity that is going to generate going to the powertrain, and the water will be delivered upstream. Okay. So this is the thing of structure of Honda battery electric vehicle. To fuel stack or how this powertrain is there. So to get just to give the idea, but except the powertrain part, I don't have any knowledge on the fuel cell. Okay, so just to give that, what is this fuel cell? How we can generate this? Okay, so you have to have some hydrogen that is input to the fuel cell, which is hydrogen, and then reacts with the oxygen. And we're going to generate electricity at this point, and hydrogen is coming down, and it also requires storage, and the water will be the outcome that is required. Okay, so here the process that is happening, the chemical reaction and anode level and cathode reaction. So 2H2 plus O2 that you are going to supply, it is generate the water plus the power of electricity that is going to generate. This is what a fuel cell which is happening inside a fuel cell vehicle. So now the question that we have is the same philosophy that we can use. So if you reverse this process, fuel cell you will have electrolyzer. So what is the operation? To take a water, give an electricity, and it generates hydrogen plus oxygen. So now we need to have water, and we need electricity to generate hydrogen. So the question is, where do we get this? What mode of electricity you can use to generate this hydrogen here? Now there are different ways that you can do it. So you can have directly irradiate from the grid, or you can do it with the renewable energy sources. So now from this, we're going to understand that we'll move into the requirements of electrolyzer, where our focus is more on generating hydrogen. And to understand this principle, that is electricity plus water is going to generate hydrogen plus oxygen. So this is what we require now. And what for the electricity get this hydrogen. So that should be our main part. Okay. Okay. four types of technology. Proton exchange membrane, alkaline, ion exchange membrane, and solid oxide electrolysis cell. So these are the four different types. So there are some parameters that we should consider to compare these electrolyzers. One about what would be the current density and what will be the voltage output that we are going to get, or operating temperature required, and what will be the stack. Okay, so if you see here, the normal current density is 1 to 3 amperes per centimeter square. So that will be the current density that we execute. But what we expect that to be around 4 to 6 amperes. If you have the same volume, it should generate 2 to 3 times more current. Okay, so here the output voltage is 1.4 to 2.3, but they are expecting that it will be 1.7 volts. Okay, if you compare conventional batteries of lithium ion, what would be the cell battery cell? That is 3.7 to 4.2 volts. But the single fuel cell stack or electric stack is going to give only 1.5 volts. Say 1.5 volts. Okay, to meet the required voltage, example of 100 volts or 200 volts, cells and make it into stack to get the required voltage. But the problem that we're facing with the battery, because the battery output voltage, so output current will be how much? A cell
Maybe 4,064 amps.
cell level will get 0.5 amps to 1 amp. So here we expect the 4 amperes per centimeter cube. That means you can able to get 4 amperes. That means the current capability reading on a the next number of fuel stacks, fuel cells are going to connect them in parallel. Okay, so here both can has to be connected in series to get the required voltage, less the parallel stacks. But battery is the opposite. So that's why I have referred this as a basically current source rather than voltage source. Battery as a voltage source. The fuel cell is able to make it as a current source. Okay. So that's the difference. So when you interface that way motor, you need a power electronic interface. You have to select your power electronic interface which converts a DC to AC should be meeting this source requirement as well as the load requirements. So the power converter should be designed like this. So it would be good if something has a more a current source given. That means you should have some inductor that should be connected to the fuel cell so that you can able to reduce the ripple current ripple on the fuel cell, which will improve the battery, which will improve the life of the fuel cell or an application. Okay, so that point should be there. Typically, you need something like current source driven topologies for a fuel cell applications or the application applications. So whatever that you are connecting to a fuel cell, that should be a current source, or whatever that you are connecting to electrolyte, that should also have some current source. That means the inductor should be connected to both of the cases. Okay. Even for the battery also, it is also similar to that to reduce the current. But however, the topology that you can select here, the current source based topologies, where battery you are going to have more voltage source based topologies. Because the voltage is very steep there, where the current is more steep here. Okay. So the other variant, this is around 0.2 to 0.8. Now they were expecting that 2 amperes, and the voltage range is also same, and the temperature and the stack efficiency they are going to talk about not in the percentage. They are going to talk about with respect to how much kilowatt per kg it is going to deliver. So this is something different because when you talk about efficiency, it should be in terms of percentage or it should be 17-18%. But here we are going to talk about with respect to kilowatt per kg. That is in terms of what is that unit? It depends. Kilowatt hour per kg means energy density. So we're going to talk about stack efficiency with respect to energy density. Okay, so here also there is another part. So you can see that based on the operating temperature, based on the stack efficiency requirement or the normal current density requirement, you have to choose the appropriate fuel cell or fertilizer for the particular applications. So it could be a stationary application or it could be a mobility applications. So for transportation, you need the stack or fertilizer may travel with the vehicle, right? So this is the mobility application. But if you see for the grid connect applications or whole generation of hydrogen, it is a stationary application. So you have to see that based on the mobility or stationary applications, you have to see about the normal current density, stack efficiency, and operating temperature that you are going to maintain. Okay, so these are the important points when you look into the and selecting the appropriate fuel cell or an actuator for your applications. So these are the key parameters that you should look into. Okay. So now the question that we have is we want to generate the hydrogen. So how are we going to do that hydrogen? This is one of the example of how we can have a fuel cell refueling station. So you're going to have hydrogen that is generated outside and you're going to store it in terms of tanks, and we're going to have a roller here, we're going to supply that. It is going to supply hydrogen to the scale it is like a fuel tank where you can push and you can, there is an onboard storage of hydrogen here, storage tank where it is like a gas you can. Okay, so this is what we are as a fuel refilling station or fuel cell refilling station, which is similar to what we have in petrol or diesel pump. Okay, so but what we need is we need an hydrogen to be generated, to be stored in this tank. So that is another important aspect that we should do this. Now let's see that what are the different ways that we are going to generate hydrogen. I'm not going to talk about the storage. Storage will be something different. Most chemists or the chemical engineering people they will into the what are the different ways of storing hydrogen. Okay. So now as an electrical engineer, I would like to focus more on how to generate hydrogen. That should be more of doesn't cause any environmental condition, which could be recycled and or it could be not cause any environmental concerns. So that would be my focus of this talk. So now the question that we want to have, we want to generate hydrogen. I mentioned before, to generate hydrogen, water, we need water and hydrogen electricity to generate hydrogen. Okay, so now let's see that what are the different ways of generating methods of hydrogen. I think the same thing would have been discussed in the previous talks as well. So one, naturally you are going to get a hydrogen that we call as a hydrogen. Okay. So from the natural gas, coal you are going to have doing a gasification, you are going to get a brown hydrogen, and you may have the or you go with a SMR, which is a steam membrane reforming, or the carbon capture or storage, which is just 6 years. This is SMR. So based on this, I can able to classify that into red and blue. Okay. So you can see that the blue hydrogen is very popular in Australia. So they are going to generate hydrogen based on this using SMR and 6 years. Okay. So blue hydrogen is one important way of generating hydrogen. You are going with this. Or there are gray hydrogen. Gray could be a represent A or G, because it's a British and American English. It's going to vary. Okay. So these are the other types of hydrogen that you are going to generate. Okay. So here I would not like to focus on all these aspects because these are all mostly to the a chemical process. So most of the chemical engineers or chemists, they are going to work on generating or biofuel engineers, they are going to generate hydrogen based on this gray or blue hydrogen. So these are the two popular. So most of the chemistry, they are going to generate hydrogen to this. Okay. So I'm going to focus on electrical engineers, but I would like to focus on electrolysis process. Okay. So electrolysis process, where I am going to use hydrogen. So water plus electricity to generate hydrogen plus oxygen. So I would like to focus on this aspect. Okay. So that means if I go for this process, I have three variants. So if I generate that using a nuclear power or nuclear energy, I would call it as a pink hydrogen. And if I go with taking whatever electricity from the grid, or you take it from residential socket, or you take it discom, or in transco you take it from power, then you can call it as a yellow hydrogen. That means it is a similar a grid connected system using a power electronic way or a conversion systems where I need to generate a hydrogen from this. Okay, so let's discuss this how a conversion process. But if I take anything electricity directly from grid, I will call it as a yellow hydrogen.
It will cause is their nature is different. Hydrogen is same. But
Hydrogen is
generation of we will call like that. Based on the input electricity we are taking.
Okay. So the process that we are going to have is electrolysis.
Yes.
Here there is a quantity of hydrogen is different when you go with an electrolysis process, and if you go with a chemical process, the hydrogen is different. But when you traditionally go with electrolysis process, only difference that you are going to get how to where you are getting the electricity. So either you get it from directly from the grid, you take it as yellow hydrogen. If you take it from the nuclear power plant, you call it as a pink hydrogen. When you use it from the renewables, solar or wind, we call it as a green hydrogen. So the only difference is that. So anyhow, we are not going to talk about the nuclear power. So we will be focusing on two types of generation, which is yellow and green hydrogen, where we are using the electrolysis process, where we need to generate electricity by these two ways to generate hydrogen. Okay, so I hope you are clear. Well, we are going to focus more on yellow and green hydrogen. Okay, so if you talk about this global or national hydrogen production, so most of the things will be of either gray. I can use names gray or gray. Okay, so it could be of 62% actually, but we may expect that 46% has to be done by gray. And the SMR process and blue hydrogen, SMR and CCS process is around 27% are occupied. But in future, we are also expecting that 11% more from the blue. And if you see the content from the yellow hydrogen, that is 4%, and green hydrogen is 5% as of now. And other process by either pink or the brown, that could be around 2%. So we are planning to focus more on 34% now on yellow and green hydrogen by next 4 years. That means we have had 9%, we want to have 34% more from the yellow and green hydrogen. Okay. So with this, the government of India forms a mission, which is our national mission on a green hydrogen. So their requirements, they want to have 5 MT, that is metric million tons of green hydrogen that should be produced annually by 2030. So I don't think so we're going to reach this at any cost, not even a one. But this is the target. I don't know, maybe this will be of 2047. And we will want to have 6 lakh jobs by generating hydrogen, but I don't think so, not even created not more than 100 or 200. Okay, so they want to reduce the import bill or the consumption of fossil fuels, which we are taking from that crop. So they want to reduce that. And also the green emissions also they want to reduce, and there should be more of generating from the renewable energy sources rather than from other process of manufacturing the hydrogen. So this is the target, and also their exploration of hydrogen. They were having the two strategic things, focusing on strategic innovation for the green hydrogen transition and development of green hydrogen hubs. Okay, so they focus more on the policy and regulatory framework and more into the demand creation of hydrogen and developing infrastructure for the hydrogen, and also that generating a fossil fuel hydrogen stations. So these are the four pillars that they want to have for the Vision 2030 on the National Mission on Green Hydrogen. Okay. So with this, they have also created the hubs. There are 3 hubs, especially one hub is comes to our Chinna. So IT Madras is extensively working on developing on green hydrogen. Okay, and there is also one port was dedicated to Gujarat. So this is Gujarat, Tamil Nadu, and Orissa. So the first part they have created the hubs. So these are the 3 green hydrogen hubs. The Ministry of New and Renewable Energy and has initiated the National Mission on Hydrogen. Initially, they planned creating 3 hubs and they gave the funds developing this. And also, the Tamil Nadu government also has given the agreement with the central government, the IT Madras. They are creating the first extensive, massive green hydrogen hub in Tamil Nadu. We want to have significant hydrogen production, and that we want to do it more with the renewable energy sources, the green hydrogen. So these are all some of the initiatives, and this definition has been given for green hydrogen. So what is the green hydrogen, and what type of hydrogen we call it? So this hydrogen we have to develop using the renewable energy sources, either solar or wind, not utilizing any fossil fuels. We don't want to use any fossil fuels. The process is same. What is split into hydrogen and hydrogen using electrolysis process. That means how to generate using water electrolysis. So means I have to have a hydrogen electrolyzer. So for that we need to have an electricity. That electricity has to generate either from solar. So this is the first definition that we should have. And the second thing is, as per the standards of government with respect to emissions, the emissions should be 2 kg, less than 2 kg of carbon dioxide equivalent for 1 kg of hydrogen produced. If you generate 1 hydrogen produced, so the emissions of CO2 should be less than 2 kg. So this has to be fulfilled, otherwise you may not call it as green hydrogen, even though you use either solar or wind to generate electricity, but this clause should be fulfilled. Otherwise, we will not call this as a green hydrogen. And you can also generate green hydrogen using biomass. So biofuels, biomass you can use or agriculture waste, but the limit is this should be fulfilled. The emission should be less than 2 kg of carbon dioxide equivalent for 1 kg of hydrogen. So movement you meet this requirement, then you do it with the solar or wind or biomass, you can able to call it as a green hydrogen. So I Roorkee are working significantly on green hydrogen generation using biomass. So this is the important thing. Moment you fulfill this condition, you will call it as a green hydrogen. Otherwise, you generate electricity using generate hydrogen using a normal electricity, we will call it as yellow hydrogen. Okay, so let's see this. What is the requirement? If you use a source, either from the grid or renewables, or you should, what would be the requirement from the electrolyzer? Okay, so electrolyzer you are going to consider as a load. It is similar to what we are talking about the sessions of the charging infrastructure. That means when you see this yellow hydrogen, it will be the same as a charger. So instead of battery, you replace with an electrolyzer. So I need not to talk about anything about hydrogen. It is similar to a battery charging infrastructure. You replace a battery with an electrolyzer process. So that's why I have also entered into this research area because I have an expertise on battery charging infrastructure. Same thing I can apply for the electrolyzer. The only difference is the load characteristics are different. So if you see on the battery, what are the load characteristics? And you're going to apply the charging techniques like CCCV charging techniques, right? And you have to analyze what are the current and voltage requirement, how you can able to pump current to the electrolyzer so that I can generate a hydrogen motor. Okay? So here, when you see the load characteristics, what are the requirements that we require in this electrolyzer? So I would like to have a continuous operation. I would like a continuous hydrogen generation. That means I don't have interrupted hydrogen. So uninterrupted power supply is required from the grid as well as I could be able to generate hydrogen here. That is not the case in the battery. That is when you require charging, you will do that. You don't need worry about this continuous operations. So there the makes it significant. And they the life of the electrolyzer depends upon how much current that you are going to pass and what will be the ripple current in the current. So the ripple current in the current should not exceed 5%. That should be at 2.55% would be the ripple that you should maintain. That means whatever the interface that you are going to have, that should be within these limits. Okay? And the other important thing that we should look into the stack life. So battery is also looking into the life, but it is not going to operate continuously for the charging and discharging area. But the electrolyzer will be like a continuous production. That means it is going to operate all the time. So we have to develop some kind of fault tolerant or redundancy system to promote the continuous operation. So that is the requirement that we should. And of course, the efficiency we are going to talk about here. It is not about the conversion efficiency, it is the stack efficiency. That means how much amount of energy that I'm going to require to get the hydrogen generation. So that is an important aspect. That means it takes less electricity to generate more hydrogen. So that is another important thing that we will look into the stack efficiency. Okay, so these are the important things that we require from the electrolyzer perspective compared to the battery. Okay, so here you can have a source like a grid, and you can also have a renewable sources. So when you have a grid, so I DC at this point, grid has an AC power conversion system which converts from AC to DC, and I have some requirements on the electrolyzer part. I need an additional stage of a DC to DC. It could be an isolated stage if you don't have a transformer, or if you have transformer, and transformer can provide an isolation state. Then typically a yellow hydrogen generation where we take electricity from the grid. And similarly, it is an AC to DC and DC to DC converter, which is similar to a battery charger. So yellow hydrogen is similar. There is not much change. I can use an AC to DC and DC to DC. So the same configuration, I can use a PFC cycle, I can use a dual active grid or phase shifter switch converter that can interface with an electrolyzer, and I can able to generate the electricity. There is not much difference. And the grid requirement is also same, and THD and unity power factor we have to maintain. So THD should be less than 5% based on IEEE 500 standards. I think Dr. Harish is going to discuss in detail about this configuration in AC to DC and DC to DC. What is the required from the grid? The same thing that you can apply here. Okay? So there is another aspect that when you generate from the renewable energy sources, solar and wind. Solar, you will have DC, so I can have a DC to DC conversion stage, But if I use the medium, the output is a variable AC. So I have to convert the variable AC to DC. So I can do it in single stage or I can do it in multiple stages. Okay, so that's the requirement in terms of power electronics circuit. Apart from this, we will also standard, we will also see in the microgrid. So microgrid also can have a DC bus. You can have a multiple actuators connected to that. There are not much challenges here with respect to power electronics. The only thing that we should do here, how to choose the appropriate power electronics system to meet the requirements of the actuator and how to control them to have continuous operation. These are the two important challenges that we have with respect to power electronics and nothing much. The infrastructure, if someone is the manufacturer of chargers, they can also develop this LO or grid manipulation systems. And those who are also marketing the solar, wind, renewable energy sources, they can enter into it. For example, Geo, Tata Power, they all can be entered into this market. So there is not big things. Only thing is you have to come up with a good power control system and take out. That's what my topic that is mentioned. The power control system control for LO and defense. So I hope you are clear with this. So I'm going to classify this based on the way you are going to connect and how much scale that you are going to generate. Suppose I want to 10 kilowatt, right? It is similar to the 10 kilowatt solar systems. Like you have an extension group of farms. So that comes under small scale hydrogen generating systems, where you are going to use the AM or PM analytical systems, where you are going to use a converters discrete components. So I am going to come in detail. And 500 to 100 kilowatt, we call it as a residential or a small commercial systems. We are going to use the AM and PM also. And then where we can connect to LV or 400 volts grid or like TV grid. And 100 kilowatt to 1 megawatt systems, I am going to get either with the renewable energy sources or I can go to medium voltage grid. That is 38 kV discom. You can connect. We call as a medium scale industrial and scales. So 1 to 5 megawatt system, we are going to use a large scale industrial and with the renewable energy integrations. And if it is more than 5 kilowatt, we are going to have some utility scale hydrogen generations. The bigger plants, like you can call as a hydrogen generation park. We have solar park or hydrogen park. Something like say utility scale systems. The bigger levels, you can either engage on a transmission system or a distribution systems. I will just grid or a renewable system. So I can classify the tasks in this case. So let's see that what are the operational hydrogen that we available globally as well as in India. So you can see that there is a plan in USA, Germany, Netherlands, Japan, Australia. So they are going to have a rate between 10 to 25. That means these are all called utility scale hydrogen generation systems. Okay, so they are started operation from 2022. And India also we have some of the things. There are 5 plants. One in Rajasthan, Rishikesh, Kochi, and there the ratings are very less. So only Adani of big plant, which is of utility scale, which of 5 megawatt. It's from operation from last year. So rest of them are very small scale, 0.25, 1 megawatt systems. So this will come under this large scale industrial system. Okay, and of course there are small scale generations, but until unless you have some systems where you want to generate, then you can have this hydrogen. For example, if you want to have a charging infrastructure, I don't want to rely on the charging infrastructure on the grid. I can use a fuel cell and I can generate hydrogen for that battery charging infrastructure. That's why I mentioned that the mix could be a solution where you can have a large production of hydrogen that also can be used for the future generation of this battery charging infrastructure. Where instead of going with the solar or wind, I can have a fuel cell as a source. I can able to do with a charging of light. So that would be a future thing that I can also focus on. So there are other operational points which are some kilowatt. So these are small scale systems. Some are India and abroad. So India also you can see that predominantly high, and because of national mission on hydrogen, so people are trying to get more of hydrogen plants. Okay. So now let us see here power systems. We will simply say that if you have a grid, so whether it is a utility scale or industrial scale, so I need to convert them into simple AC to DC and DC to DC, and I can have it there below. So basically, this system is going to generate electricity required to generate hydrogen here. Okay. So if you have anything like a solar, so I have DC, I may need to have a DC to DC converter. So you can have an electrolyzer. So here, if you have a transformer here, so you don't need an isolation otherwise. With two dotted lines, that means it is an isolation. Okay. So I can have an isolation if you don't have a transformer. So it is going to provide an power isolation. The reason is required. If any fault happens on the grid, it will not go into effect on the electrical part. Any fault happens on the grid, the electrical it will not affect on the grid. Because we should have a separate loads. If we don't have separate loads, there will be chances of some kind of circulating current that can influence the other. Okay. So that's why we need a power isolation is required for this kind of system. So either you do it with a low frequency transformer or a power transformer, or you can have a medium voltage, medium frequency transformer. So this we're going to call it as a solid state transformer. So short form we can call it as a system. Or a call as a power electric transformer. Okay. So this is the requirement when you go with a renewable. And for example, if you ask me, you may also have an AC to variable AC to DC conversion instead of DC here. But the requirements that we have is this DC to DC converter should be able to control the current and the voltage required by the electrolyzer, and the main motive is to reduce the ripple so that you can improve the direction of the light. Okay, so that is the other important thing that means the control of the additional DC to DC converter is required at this stage. This DC to DC converter is a power production circuit, so which is required for the grid to maintain PHP less than 5% and unity power factor that we need to maintain. Okay, so here other important thing that we should also look into that when you use the reason why we are doing the solar and wind, the solar is predominant in daytime and summer, and wind energy is predominant in winter and night. Okay, so if you mix both of them, I can able to get a good combination of that. I can able to get uninterrupted power supply that we are going to generate by the place. Another important thing, we also should have some kind of an energy storage system to store the energy also you can able to generate back to the electricity that is required. Okay, and this energy storage that we going to use it is not the existing or like the new one. We want to use this battery, which are the secondary life of the batteries. That means the batteries which is already utilized for electric vehicles. So when you recycle it, and you can also use for the stationary applications, which you call as the secondary life of the batteries. That secondary life of the batteries can be utilized in this hydrogen generation systems. So this makes more sense. It is a one kind of what you call not a unidirectional economy. It is a circular economy. That means we are trying to utilize the process what we are using for batteries and electric vehicles. Then we are going to, once it reaches 80% of its capacity, we consider that the batteries for the battery powered vehicles. I am going to take the battery, recycle it, and I can able to generate a battery that can be used for the stationary application of hydrogen generation. So that I am not going to waste my material, I am not going to impact the environment. In the way, we call this as a circular economy. So in academics, this is very important. It should be of circular economy, and even the power electronics converters. Now we are going to talk about not direct economy. We would like to call it as a circular economic based power electronic systems. So it means even we are going to use the power semiconductor devices that can be recycled and that can be reutilized for the power electronics converters. That means we want to eliminate the e-waste. So e-waste also should be eliminated. So that's the other important power electronics to want to work on power electronics field. So the now future trend is to avoid the e-waste, convert them into recycle and utilize for the power electronics systems. There are different mechanisms, methods that can be used for power electronics systems. So there are some applications where you don't remain such kind of power electronics. So that can be utilized for such power applications. So I have made clear proper questions.
Sir, is it not possible to use the recycle patterns for recycling?
Because it will use the characteristics of components what we require. So that's why we're going to use that for the stationary applications. You may get the energy density, but power density you may not. So that's why we cannot use for the mobile applications. Only stationary applications. So any questions? So now let's see that what are the powerful converters that I can use. So now I am going to focusing on the yellow hydrogen. So yellow hydrogen I have a conversion from AC to DC state and DC to DC. Let's see that what are the different types of converters that can be used as AC to DC and DC to DC. So what is the functionality of AC to DC converter here? So here the functionality is to maintain the DIT less than 5% and unity power factor on the grid side. I want to get a stable DC link on the output. So that is the functionality of an AC to DC. Let's see that what are the things that we can have. I can use a simple diode rectifier, but simple diode rectifier may not be sufficient, where it can able to act like a nonlinear load in the grid. So you have a unity power factor. That means you have to have a power factor connection set. Okay, so that I can able to get with kind of an active passive filter or an active filter. That means add one LC circuit or use some kind of an active power electronic circuit to get a unity power. Or you can use something like a multi-pulse rectifiers. There are a combination of multi-pulse rectifiers where you can use the harmonic cancellations. The lot of harmonics can be eliminated here. Okay, so for these applications, what would be the multi-pulse rectifiers? I hope everyone knows about multi-pulse rectifiers. Anyone? So what is multi-pulse rectifiers? So I am using a diode rectifier. I am going to use the sum phase shifted by the transformer so that I can eliminate some of the anomalies. Okay, we will have 6 pulse rectifier, 12 pulse rectifier, 18 pulse, 24 pulse rectifier. So if you use that part, I can be able to eliminate the lower part of harmonics so that I can be able to achieve the TSD less than 5%. So other advantage is this multi-pulse rectifier is going to use a phase shifted transformer provides the inherent isolation. So I don't need an isolated DC to DC converter state. I can use a non-isolated DC to DC converter state. Okay, so this is for high utility applications, high power utility scale applications or industrial scale applications. So I would prefer to use something like a box or this diagram rectifiers for high steps, so which are very robust and well matured in the technology. So in BHL we have manufacturing of diodes, we have manufacturing of thyristor. So it's better to use a multiple rectifiers as a AC to DC conversion stage. So that's why AC to DC conversion I will have this kind of configuration. Or I can use a simple two level voltage source converter. Can be an active converter. So here I am not talking about the single case because we are not looking like a battery charges where we can get it from the residential source. So here we talk about only three-phase systems because hydrogen production should be more, and we were focusing on industrial or scale hydrogen production, not on the hydrogen production on our residential home, right? So we are not worried about the single-phase connection; we are worried about the three-phase connections. So when we are worried about the three-phase connections, we have an option for multiple rectifiers, or I can have a two-level voltage source rectifier, or I can have a multi-level AC to DC converters or rectifiers to create a possible solutions for this. So the main requirement is for applications based on the voltage level, you can utilize a multi-level converter field. So one of the research area if you want to use for this yellow hydrogen of AC to DC, you can work on something like a multi-pulse rectifier or multi-level converter from the AC to DC conversion stage. Okay, so I'm not going in details of problems. I'm just what would be the different types of converters that we can use. Okay, so I made some comparison about what would be the topology. So there are different types of topologies that we do, and what are the control type based on classification that we know that. Uncontrolled is the diodes, semi-controlled is the thyristors, or fully controlled, you can go with the MOSFETs or inhibitors. What would that means be when you use a type of converters, and what would be the power that we need to achieve, and what will be the complexity of the manufacturing or assembly, and the control, and the you will see here, if you use an active neutral point or neutral point converters, multi-level converters, to achieve the TSD less than 5%, or power factor is more than 0.8. That means it will be a good candidate. Or using 24 pulse rectifier, I can able to get less than 5% TSD, and I can able to get more than a 0.8 power factor. So these are the two possible things. Candidates as an AC to DC converter. So now let's see that what would be the possible DC to DC converter. So already we have a phase shifted transformer. That means isolation will be provided by the transformer. I don't need to have a non-isolated state on the DC to DC converter. I can use a non-isolated DC to DC converter for this case. So what kind of non-isolated DC to DC converter I can use? So everyone knows about non-isolated DC to DC converters. Buck converter, push converter, buck boost converter, septic converter, beta converter. What else? Chuk converter, septic converter. So I can use all kinds of converters. But what would be the requirement I should have? I want to have a smooth current on the electronic cell. So I should prefer something like have an inductor on the electrolyzer part. That means I cannot use a boost converter because I will not have an inductor on the output side, it will be on the input side, on DC side. So boost converter I cannot use. A boost converter also I don't have an inductor. So option I have is buck converter. Buck converter I can use for this application. So I can use the buck converter. I can use the interleaved buck converter so that I can go for a high power rating. So what is the interleaved buck converter? Two buck converters or several buck converters are connecting them in parallel. Give the pulse to the derivatives such that I am going to get the cancellation of the ripple. So that means ideally you generate ripple, inductor ripple for one you will generate inductor for other ripple like this. That means you can see the cancellation of ripple. That means actually you are going to get flat current on the output side. Right? So for that, if I go with a different channels of a buck converter, it would be good and I can able to get less people on the output side. Okay? There are other converters people are also starting with rich configuration and going with things and they are able to get a 4 switch split capacitor based and there is a tapped coil based or quadratic buck converter or tapped buck converters that they are using. Okay, so their examples are tapped inductor buck converter, quadratic buck converter, switch inductor capacitor buck converter, stacked buck converter, interleaved buck converter, and extended duty cycle based interleaved buck converter. So if you want to use a non-isolated converter, you have to use a buck derived topologies. So you can come up with new converter topologies based on the requirement. The possible DC to DC converter should be a buck derived DC to DC converter topologies to be used in this case. So you need not use this, you can come up with new buck converter configuration based on the requirements, understanding the requirements on the electrolyzer profile. Okay? So is it clear? So when you want to design any converter, you should understand the load characteristics first. So based on load characteristics, I have several DC converter, which DC converter I should use. So requirement I should have on the thing output side so that I can be able to reduce the ripple on the output side. And what are the different types of a DC to DC converter I can use? So I can make the all the buck derived topologies. So these are the possible use as a DC to DC converter or a transformer plus a different DC plus a DC to DC converter. For example, if you don't have an isolation on the AC to DC state or before AC to DC state, that means I need to provide isolation in the DC to DC state. Okay, so in this case, what kind of thing I should have? This also I should have a buck derived topology, but isolated buck derived topology, and also I need an inductor on the output side. Okay, so here you can see that the possible cases I can have with the half-inch configuration, or I can have a resonant converter, or a phase shifter for boost converter, or a dual active boost converter. And dual active boost converter, you will have supply. But do you really need a bidirectional power supply for this application? Because you are not going to power back to the grid like when you use for the batteries, you also have an option of vehicle grid or vehicle X. But you don't have an option here. It is only vehicle to hydrogen generation. That is the power to H. So we call this as a power to H, where you need something like a bidirectional converter. So unidirectional converter is going to serve this purpose. You can see that the same application, same expertise what I have, we are going to analyze the requirements and we are cutting up all the possible options. See, I have many converters which are required to be prospect to use the converters. From the load side, what the converters are required, one of those converters. In this DC converters, we have a lot of options. We need to convert to only buck related topologies. And also that, for acceleration also we have a buck related topologies. And we don't need a bidirectional aspects here. Unidirectional converters. So we need not to worry about bidirectional converters. So you can see that there are all things, and finally we're going to analyze what could be ripple content and what could be the voltage gain that we are expecting, because there you're going to have a voltage step up or step down happens from the grid to the hydrogen part. You have to look into that what kind of gain you are expecting based on the state that you are using, and what would be the efficiency of the converter, cost, and here reliability also very important because we want a continuous operation here. And the other thing is current handling. So the current handling is another important thing. Whether you are using a multiple channels, for example, a buck converter, the current sharing between all the lengths should be the same. They should not have any mismatch in the current from each leg, so that you will not have any circulating current. If you have circulating current, it is also going to affect your efficiency of your power conversion states. Okay, so based on all these subjects, we have come up with this proposed configuration, which recently published in Active Transaction Tolerance. So we studied all the converters. We finally going to the 12 pulse, 24 pulse rectifier. We analyzed all the requirements. So 24 pulse is good. We are able to get 5% THD, but all operating conditions. So I am not worried about only one operating condition because I want to do from one parameter power supply to 0.1 to 1 parameter. That means if I design my hydrogen plant with a 1 megawatt, I need not to operate at always 1 megawatt. I can have, based on the availability of the electricity, I may operate at 100 kilowatt as well. So in this case, operation from 0.1 to 1 parameter, right? So that means if I select all those things, I should operate in all these operating conditions. So this is another important point that you should know that. Okay. So once you know this part, that means we made an analysis for all 6 pulse, 12 pulse, 18 pulse, and 24 pulse. We found that the 24 pulse is good, and it is going to have accuracy less than 5% from 0.1 to 1%. So based on that, we finalize going with the AC to DC converter. And when you are gone with the 30 pulse, you may get still a better protection in the THD, but considering the transformer design, the phase shifted transformer design, and also the cost of the transformer and efficiency of the transformer. So these are all points become ready to our account. Choosing a 12 pulse rectifier, and then we followed by channel a reconfigurable interleaved buck converter. We have gone with a interleaved operation, interleaved buck converter, and should be reconfigured. Any reason why? Why do we need to have any reconfigurable channels? Is there any advantage? And why should we go with interleaved operations? So, how do we discuss the DC to DC conversion case? Several DC to DC converters are there. Why should we choose an channel interleaved buck converter? That means buck converters are connected in parallel, and we are going to switching operation based on 360 degree by n. So means if you are doing a 2-channel buck, 360 by 2 means 180 degrees. Phase shift between the both the buck converter, so that we can reduce the ripple cancellation. So if you are 3-channel, 360 by 3 is 120 degree phase shift. For example, if you use a 6-channel, 360 by 6, 60 degrees phase shift, I'm going to get the ripple cancellations. And the moment you are going instead of using the topologies, quarter of arc and all. We want something for high power level. When you're going with high power level, it would be some megawatt range. So when you talk about megawatt range, simple buck converter should not have a current. The voltage is variable, current is variable. So single power current devices will not get. Right? So we have to use them in parallel so that the current scaling can happen along these channels. So based on this, I am able to design a channel NVU power converter. Okay? And why we need a controller because we can also operate at partial load conditions or half load conditions or full load conditions. That means I can operate at 0.5 variant and 1 variant. So if I design power converter, still I need to operate at 1 variant. I may not able to get the required operation. Okay? So for this, it is always good to have an channel, and I should have developed a control strategy to configure the buck state because the front end side we are not controlling anything. It's uncontrollable. So my DC link is this. I have flexibility in controlling the buck converter side, and I need control strategy which effectively control this based on the efficiency and the ripple requirement. Okay, so the ripple that is directly proportional to the life of the algorithm. Okay, so considering that we want to develop some kind of control systems, so I can generate systems. So I want to have a DC link control. From the DC link, I have a PA controller, I have a gate guidance with the connectors, or the control that we are doing normally. Or I can have an active front end converter. We use the front end converter. I can have a DQ control over this, the voltage front end control. I can control the DC link across the 2 level voltage source converter or a manual level. And DC to DC sets, I have a 2 requirements. If I have a non-isolated control, I have to control the duty. If I want to use the phase shifted control or isolated control, I should have a phase shift and have to control it. That means I need to have a phase shift as an output or a duty signal. And what is the requirement? I have to control the inner inductor current and the outer voltage. So outer voltage loop and inner current. So that is what I am doing for the DC to DC level control. They have DC to DC control. We are going to look output inductor current as well as the capacitor. Because we have a 2 energy storage elements. L and C, I have 2 state variables, IN and DC. So that I need to control, and I have 2 outer loop and 1 inner loop. Okay, so now the problem is the conventional thing. Here I want to use for the output and power rating, right? So I can use the partial load operation, I can go with 1 bar. So if you want to use this wide power range, I have flexibility of using a conventional API control system because I need bandwidth and I cannot able to tune the complete system, right? So because of that, I should use a system where I can able to track these changes and I can able to control this part. Okay, so further we want to learn something like predictive control approach where we started understanding the model. So predictive control, the model predictive control, which going to depends upon the model where the switching states will be generated or duty cycle is going to be generated by future state prediction and we are going to control that. Okay, so we have to have a predictive model that we develop. That means you should understand the model and you have to develop a state space model. So you start with the state variables, you have a IL and DC and draw that into a state space model. X dot is equal to X plus BU. I have A and B state matrix and the output matrix that you can generate and you can develop a model of the field and that can be used as a predictive model for the predictive control. And I also mentioned that I have to predict the future state. So if I want to have an IL, that predict the if I want to do a K state, I want to predict a K plus B state so that I can generate the reference. Okay, the reference generation we are going to use a Lagrange extrapolation use the second order or third order systems where the feedback that I'm going to generate and the model that I'm going to get this characteristics. Okay, so now we're going to define the cost function. I want to remove this the outer loop. Sorry, inner loop. So the outer loop will be I can represent IL star. This is the error that we are going to get. So this I am going to define as a cost function, which is as a cost function. So I want to minimize this so that I am going to get the switching state of this interleaved buck converter. So that we are going to achieve with the training. Okay. And second part we are going to use the same loop because in the loop we need a fast dynamics or fast dynamics. So this is required in slow dynamics. So since we have a slow dynamics, we are not worried about this outer loop, but in the loop we are going to focus on the predictive loop. Okay. So our aim is to focus on this. Whatever we have in a control or a linear control system, we convert them into a predictive control system. Okay. This I am going to define a cost function. So I am going to find all the switching states such a way that I am going to get this error result. So that is the basic functionality of the predictive loop. So when you want to get this 0, you have to do calculations. Switching state to get this, right? I need to follow all the information about that. So I have to do a future prediction of the state. So that means I want to have know about IL as the k instant. I have to predict that IL of k plus 1 instant. And you may also have something. It is almost required to have a IL k plus 1 to compensate the delay. So it is always required to have k plus 2 state. So that means I have to predict the k plus 2 state. That means you can use the mathematical use, extrapolations to detect a k instant information. You can future predict the k plus 2 instant by Lagrange's extrapolation. So that is what we are going to do. That first we are going to analyze that what would be the model of the interleaved buck converter. So I have used the two states. One is IL state variable, so which is ideal by L. So I can able to get the same thing in some switching function. Okay. Then using a this is a what you call as a continuous state model. Continuous state model. So I'm going to convert them into discrete time. So I have a discrete time conversion system. Have a backward forward converter, zero or hold or modular or midpoint systems. There are different types of discrete methods where you convert into continuous time model into a discrete time. So here I am using a forward Euler method, which is simple. This you can able to get a Taylor's expansion. So you use a Taylor's expansion. If you consider only the first order, I can able to get. I can represent by here IDP is equal to y del k plus 1 minus IL k plus 1. So I can able to get this part which is equal to I can represent this IL by this expression. That means I can able to get this predict state. A k plus 1 I am going to predict. So this code would be our predicted model. So I k plus 1 is equal to ES by L into S into VDC as k instant and V naught into k instant. So VDC by k instant that you are going to measure with what is the DC link. And you know what would be the output voltage we are going to measure. And I am going to measure the IL as a k instant and based on the switching operation that I am going to select so that I can get the predicted. Okay. So what would be the cost function? The cost function would be IL k plus 1 minus IL k plus predicted. So this is gap with the predicted model. So this I am going to get we have a I'm going to use the extrapolation algorithm. I can able to get this ILK plus 1. So if I use the second state, that is k plus 2, k plus 2 I can get. So the same expression I can able to replace with the k plus 2, IL plus k plus 1, ES by S into switch into VDC by k plus 1 into V0 by k plus 1. Okay, same expression that we need to calculate. This is the iterative process. You have to do this. So now, what I am going to PA, this is a simple error. So I can able to estimate the reference. I am using plus extrapolation to get the reference k plus 16. I am going to get the actual from the model, the predictive model. I can able to get from this expression. Okay. So the main thing is that we want to make this 0. Right? So what we are doing now? So we try to make this 0 such that we are going to get this switching state here. So that switching state, the moment you are k plus 2, that switching state you are going to apply at k state. So in this case, you are able to get the optimal switching state, making it as I. So this is all about the predictive. Okay. So for this predictive control, the last I mentioned that we need to know the load also. We have to consider the load characteristics. So the replacement can be represented with the simple RC circuit. So the first one is the volts, this is a steady state part, and this will be a so this will be a dynamic. So this will be a represent the steady state response, and this is the transient response. The transient response of an analyzer represents a simple RC circuit. So I can have any electrical performance, I can simply represent within RC circuit. So the same thing for battery or the analyzer, represent within RC circuit. So this RC circuit will represent the transient, simple RC represents steady state. So we can have represented how they got this. This is only a chemical engineer can explain that part. So we can consider that one of the information there given. I can able to model that in a simple RC circuit. So we are able to model that, and the way that we are modeling it will be represented by the degradation part. The moment you reduce the tool, I can able to reduce the degradation of the electrolyte. So that's why I mentioned that I am trying to keep the ripple on the outside is at 2%. Okay, so this is what the ripple content also is a thing, very important thing. The ripple of 50H to 5H component is going to cause 8 to 10% of hydrogen loss due to the slower electrochemical performance, and electrolyte can cause up to 6%. Okay, so that means we have to be consider the current coming from this power electronics converter. We should be not consider this harmonics or from this frequency components. That is the important challenge that we have as harmonics engineer. So you have to develop your DC to DC converter systems, especially to make sure that this kind of switching components should not be generated in passive way. So that's why there is a role of harmonics engineer. This is a simple part. Whatever we have in simple AC to DC converters or DC to DC converters. Why should we give the more attention here? Because of this important method. So that means the DC to DC converter design, such application, irrespective of an LO or P. So only difference that we have LO is you have AC to DC converter, or SOR you have DC to DC converter. The DC to DC converter is the same here, irrespective of this calculation process. Okay. So we have to convert or design DC to DC converter, very crucial for this element hydrogen here. So not to have this frequency component to be passed away. So for that, what we have here, we have replaced this inner part with a predictive control. And you know the predictive control will be something of variable switching frequency. So instead of generating the switching state, we are able to generate the duty, and that duty we are comparing with the modulation state. So that we are able to get a fixed frequency operation. So that's why we are going to have a duty generation for the different upper. There are two switches, E1 and E2, S1 and S2, that we are going to generate the duty cycles. And we are going to add there is another reconfiguration state here, because how many number of channels that we need to send. Okay, the predictive control is same, but we should be able to control based on how many channels that we need to operate. Otherwise, it's simple predictive control. Okay, so this we incorporated. You can see that based on the parameters that we are calculating here, and we are going to have predictive model. From predictive model, I can be able to get IL P k plus 1, and this IL I am going to have a reference here, and then I am going to extrapolate, and I am going to get IL star k plus 1 here. This is the reference, and I am going to give a cost for minimization, which is IL star minus IL into k plus 1. And that is going to generate the duty cycle. That duty cycle I am going to generate, and that based on your interleaving operation, how many number of channels that we are going to have here. Okay, and we are also going to give the input how many number of channels we operated based on the reconfiguration strategy. What the strategy should look like? The strategy should consider the duty content and the partial load operation and consider the efficiency. So we have made some kind of analysis, and then we are able to come with this. So here we consider only a simple steady state performance, and we are not considering the dynamics in the system, because we didn't get enough information about the dynamic characteristics of Paris. So I noticed that something output relation here. So that means based on the current, I am going to measure what is the reference voltage that we are going to have here. I am going to submit to V naught by K at this point. Okay, so this information is required. So based on that, I am going to generate the efficiency matrix. So what kind of things? I have considered what is the number of channels and what would be the power demand. So based on the power demand of this expression, I am going to calculate the channel efficiency and also calculate the ripple content. So one is efficiency based search and the ripple content search. So I am getting the information about calculating the number of channels in the circuit. For example, if I want to use a particular mode of operation, how many channels that I should operate based on the, and the same thing we are doing again based on the number of channels, considering the efficiency. So now we are going to optimize solution. So based on the ripple and the efficiency, we have defined the trade-off. Based on that, I am going to select the number of channels to be present. So that would be the input is going here. So based on this, we are able to generate the duty cycles and efficiency calculations we did in the based on the power demand. So you can see that 0.21 we have changed the power demand. We found out that how many number of channels that we do. So we made with a 3-channel solution. I can operate with 1 channel, 2 channel, or 3 channel, because based on the hardware requirements, we were ready to develop a 3-channel buck converter in our lab. So we started 3, but however in actual applications, we should go maybe target about the 5 to 9 channels. Okay, so we did the envelope, what would be the duty cycle that we want, so that we calculated, we will get what would be the minimum raises and what would be the channels that we need to operate. Okay, so this is the based on the normal case current. The last part, we are able to get that part, and how we are going to generate. These are the simple steps I mentioned here. So the reference current, I am going to use the reference extrapolation. So this is the straightforward mathematical solution that we can get it from anywhere. and I'm going to use the interpreter prediction method, prediction model that I mentioned here. So with this equation, the equation 5. So this I am able to get the equation 5. We will generate like this, and we're going to cost function formulation with this aspect, and the ripple factor we add this part, and finally we derive the duty cycle that will be applied based on the switching frequency that we are going to apply. So in this way, we will generate the effective cycle using a predictive control. Okay. So we did experimental setup, we did in our phase shifted transformer and 3-channel so the 5 kilowatt system that we are going to generate and operating 5 kilowatt systems. Okay. So then we have got to the grid side parameter. You can see that in the like a output side, you can see that there is 12 pulse. Because of 12 pulse rectifier, if you use a 6 pulse rectifier, you will get 6. So you can have 6 n plus or minus harmonics that you can evaluate. Okay, if you go with a 4 pulse, the minimum order requirement is either 24 or 23 or 25 lower order harmonics that you expect. Okay. So these are some of the results. And then we are able to get the 3 operations. A buck operation for P-channel and 2-channel based on the ordinate. So here we are dealing with a lesser number of things. I can able to operate either 3-channel or 2-channel. But however, if you go to the higher number of channels, you can have a different types of combinations where you can have smooth power, smooth variation of this channels that you can see and different power limits. So this would be good with respect to utilization. So that is the advantage we can get it. So we have to see that this would be also transition from the 3-channel to 2-channel online. So what would be the impact that can happen in the systems? Okay. And also we need on the fall. If it's fall happens, how we are going to control with this. Okay. And we have all the methods which is there in the existing literature. We started with the classical PA control, and we applied the variable switching frequency operation CMTC, and we also used the dynamic predictive control approach. And finally, we propose this method. And we have seen that in the transient, when you move from one channel to other channel, the transient response is also very fast, and we don't see more of overshoot here. So the other important is move from one channel to other channel. So these kind of things, as no one has explored so far for the green hydrogen, because we have taken from the green hydrogen or hydrogen perspective, we can able to get this kind of control algorithm here. So from the power converter perspective, it is not much novelty, because based on the study, we assume that a 12 pulse rectifier and a buck would be sufficient based on the requirement. But with respect to control, this makes a good significant part. And we have featured it also done this part, because since it is not published, we are not able to do present here. But we removed this the other states, even the slow branch here. We made that completely with the predictive control algorithm. Already we have submitted it on this, and we have also explored this instead of going with at all costs. When we are using the active front-end converter, we are able to control some other control parameters. We are able to increase the stack efficiency. So it's not about the power conversion efficiency. Stack efficiency is also we are able to get it. So this we have to compare with, people may ask the questions, okay, this record is not new. Did you compare with other applications? Yes, we compared with other applications, other even for the chargers, there is also reconfigured systems. And where the design object was something different in the other cases. So design operation chargers or mobile chargers, we are targeting about the getting efficiency at remote operations. Okay, so here improve the lighting efficiency, but also increasing the transmission performance on the one mode of operation into other mode of operation, and also to reduce the ripple on the output side. Okay, so we also compare with other performance, with other predictive control as well as the classical control, and we will be able to get that it is going to have issued all the requirements with respect to settling time, output overshoot, current overshoot, and the current state reactor, the error between the phases which we are talking about, and output ripple and output current ripple is all are better than existing systems. And we are also going to get constant frequency operation where you can able to effectively design a passive component and which are spread over frequency spread, spectrum spread at one point and spreading at all these frequencies. So that is what we will to get. So I have used a day tool again, like you people, which you presented for this. So where we have what AI is going to do for the summary of the so which I claimed here. So the same thing that we are going to accelerate in the tracking of electrolysis current and what is reference, reduce current thing and more current with the low better efficiency and reduce switching losses and renewable operation. And in fact, so this could be a good solution when you use for the utility and large scale applications. So these are some of the parts that we can able to get. And also the future work is one we are not worried about it because one is on electrolyzer manufacturing part based on the catalyst or anode or cathode that we are going to use. So that the different types of electrolyzer where chemistry or chemical engineer has to focus. And the second thing they also focus on something on low cost solutions and also improving the current density, which we talk about the 20 to 30 requirements and also the stack efficiency. So that they have to focus. And from our perspective, it should be a polarized or intelligent control, which we are currently working on. It. One of the examples that I have shown here. People need to focus on the policy and regulations and things which we are also not very about it. And there is another thing that we also should focus on forming some kind of a grid. Okay, so where you going to interface the grid, renewables and storage. There is a coordination control among these systems. At the same time, you may also feature you want mixed systems, right? Whenever I have a station, it should have a battery charging system as well as hydrogen systems. So I have a mix. So people are talking about AI-driven data. So AI-driven data center is also the same configuration. You have a AC to DC and DC to DC converter. So if I have common DC negative grid, I can generate that to with hydrogen, battery chargers, AI-driven data centers. I can get a complete system that can be formed. So there are a lot of things that people should look into that. Okay, so this is all because of hydrogen generation. The other important point I should look into the storage of hydrogen. So, okay, you are generating hydrogen. How to store the hydrogen and you have to travel the hydrogen to your hydrogen refilling stations. So, during travel, the safety, storage safety, and also the operating temperature that you are maintaining that is also very important. Okay, and the life cycle assessment. And one thing that Bhimavaram has pointed out about the costs. The cost is the important thing unless you achieve all these performance, high efficiency, high performance in terms of ripple, high at the same time I want everything with low cost. I don't want to spend more money for getting the solutions. Industry doesn't appreciate. If you do, I have get 99.9% efficiency. I am getting high mean time between the failures. I am able to get a ripple. I am able to get 0.5% ripple. But I am able to get the cost is very high. Industry will not appreciate it. So we have to achieve all these things. So that is the main important aspect when we want to an academics or industry. We want to have a product. So that is the main objective we should achieve. Okay. So with this is also let's say interdisciplinary or multidisciplinary. The chemists, mechanical engineers, thermal management, or even mechanical production, and like chemists or chemical engineers or electrical engineers, or even for power electrics engineers as well as power system engineers has to work to get into an appropriate green and sustainable solution for future transportation as well as future energy sectors. So it should also incorporate battery as well as hydrogen generation and also AI driven capacity. Okay. So with this, these are some of the references that I have used for this PPT. Thank you very much. If you have any questions. Any questions? I hope I made it clear to listen. So I don't think so. Any questions? How what are the things that we will need to research? But if you want any questions how to do research, then I can answer.
Sir, actually, I don't have any question regarding the content you have told, but regarding the control part, you have explained a lot, and I need to know how much time it has taken for you to do the control part and all.
2 months. The main part that we did is the literature part. The second thing that is the problem about the requirement of or the load calculation. So when you start something, we should target about what is the load requirements. So that takes more time to understand the load so that we can design a system. So without understanding the load, we will not do that. That's why we will not understand that. First we talk about load calculations, then we will learn even for vehicle sizing also. We start with the net cycle requirements and what would be the load requirements of power or torque requirements or speed requirements. Based on that, we are going to design the machine.
Instead, electrolyzer model is a linear.
So I have considered as a linear model, but it is actually not a linear model. So there is another important thing why we call it predictive control. Is since the model is non-linear, it's always good to go with the non-linear controls rather than going with the linear controls. So we want to incorporate this non-linear characteristics also into the systems. It will be easy for us to have this kind of multi-objective as well as a multiple constraints I can do with. Here, as of now, we are using only one cost function. Doesn't make any sense with respect to using a predictive control at this point. But the main idea that we want to use, we want to include more constraints as well as more objectives that we want to see. For example, if we want to go with a material converter of an activity, have a capacitor voltage balancing that I have to use again a PA controller to do that, or I have to use a balancing circuit to do that. So instead of using that, I can use an additional cost function of a voltage balancing here and I can able to solve that. So voltage you don't see is much variation. Voltage characteristics is very that's why I told about more about so because the characteristics of current is very important. When we're talking about the current density, we have given more emphasis on the current density, not on the what is the voltage. Voltage will be in the 0.5 to 1.5 volts. There's not much difference on this. And the ripple also with that 100% will be various.
They keep only around 5% ripple. Requires 2% or even less.
So that's the little more capturing. DC to DC converters and the control is more important. Any more questions?
using basically from nuclear using hydrogen.
Yeah, that's what we had. We have no job for me to do on hydrogen. So as an engineer, what will I do on hydrogen?
You can utilize this.
Yeah, so that then they're doing that. My focus is not on that because I don't have any research on it. What is the scope of my perspective on it? I can use on another with respect to generation, I don't see any challenges on the grid side or the solar potential. Already solar systems has been developed. Everything is only thing is I would like to focus on more on actual where on that. Other than that, I don't see any challenges in the following. So I have to find out control strategies, convert to all these where I can focus on reducing the input so that I can able to have so we should be considering something on what are the other impacts, what would be the temperature, operating temperature, and what are the characteristics of that we can take it as an input, and we can able to do the natural thermal controls of present, so that I can able to control the temperature of that present.
Efficiency, the conversion efficiency from electrical to in terms of joules, if you can. If I'm using something joules for density, the form of hydrogen, how many joules?
I don't know that efficiency we talk about in that sense, because people generally talk about stack efficiency. Because if you talk about only power conversion efficiency, I would like to have 99.9%.
Joules in terms
Joules, I think it would be so mostly the energy utilized only on the I don't know exactly what would be the maybe I can look into that because not with the mostly I was talking about the stack efficiency. Maybe we are doing some calculation something. The good thing based on the joules or energy efficiency is also helpful in getting this valuable efficiency part. So when you calculate the efficiency, we can able to talk. We'll send to the mean efficiency we can find out. We can also compare different types of electric vehicles, fuel cell vehicles, and battery powered vehicles, where we can do it using the Greek model. So there is a Greek model that is there. We can use that Greek model and we can compare.
development of all these solar systems. The quality electrolyte is available.
Yeah, that's what now if you want to calculate for example, you are using a tool to generate the efficiency is 12.30%. It is 70%. Use the solar, it is 18% to 20%. So we available efficiency is very less. You cannot compare these two systems because comparing with the natural technologies. Questions? Thank you very much.
Good afternoon to everyone. Now it's time for planning and administration of Amiram Resource Person. And we come to the conclusion of this informative and enriching session. It's my pleasure to take over the vote of thanks. Knowledge becomes meaningful when educated, and learning becomes powerful when it inspires us differently. On behalf of the organizing committee and all the participants, I take this opportunity to express our heartfelt gratitude to our esteemed resource person, Dr. Deepak Puri. She was trained to a valuable time, expertise, and experience with us. Frustration on power conversion system for a yellow and green hydrogen being was not very informative. It was thought-provoking and engaging and inspiring. We sincerely appreciate your patience in addressing the questions of our participants and of our encouraging meaningful interaction through the session. I also thank all the participants for active participation and valuable interaction which made the session successful. I request our respected and coordinator and co-coordinator of the FDP to kindly come forward and illustrate our resource person, Dr. Deepak Puri, with a moment role as a token of gratitude and appreciation.
This occasion, I would like to mention, we are fortunate to have Dr. Deepak Puri from IIT Madras. Once again, today, listed here for delivering workshops. Not only that, I visited IIT Madras a few days back. If you look at the way looking at the issues the society is currently facing, it's wonderful. It's a great opportunity for all the participants of this FDP to know how actually research can be done. And useful outcome can be definitely and external participants, members of presentation and time. And
Also, I'd like to point yesterday that one of my students has also given so Dr. Hari is my student, so I have not covered charging, so he will be covering the charging. He is attending for this. I think it will be good for you to also know about the charging.
afternoon where we will have the charging infrastructure. And really wonderful work was done by Deepak and IIT Madras. You can all see all those outcomes reported in IIT transactions in power electronics. Most of the work was published in those high quality reports. After that, several patents also, including megawatt charges. It's really good here. Research directions you get are very useful. And